All right, chemistry 3111. What I said was last class we would take a look at this problem here. Question 19.5b, which it just says predict the major product for each of the following reactions. So here we have a reaction between a ketone. We have a ketone and we have a primary amine. And so when we react a ketone and a primary amine with a catalytic amount of acid, so this is catalytic, that's what those square brackets mean. And then remember this negative H2O, that refers to loss of water during the reaction. And so when that happens, we end up forming an imine. So how do we draw the imine? Here's how we do it. What you do is you redraw the ketone. Okay, just redraw the ketone. And then all you have to do is erase the oxygen and replace it with a nitrogen. And then whatever was attached to the nitrogen, put it on the nitrogen. So there's a cyclopentyl group attached to the nitrogen, and don't forget the lone pair. So if you're like, well, where did the two hydrogens go? Let's think about that. You lost two hydrogens and an oxygen. Ooh, what does that make? That makes water. So that's where the water came from. So this would be categorized as an imine. All right, give me a thumbs up if you're with me on that imine formation. Everybody, does that make sense to everybody? My strategy, cool. All right, so the next one I said was predict the product of this reaction. So it's 19.17b, and I said that this is the reaction between a ketone. So we have a ketone. Remember, it's Ketone, not Key. So this is a ketone. I told you the NH2, NH2. So if you have NH2, NH2, this is called hydrazine, hydrazine. And then from hydrazine, you can make a hydrazone, okay? But you can treat it just like it's a primary amine, and you can just imagine the other NH2 group as being an R group, okay? You could just treat it like that and make an imine, and you're gonna get the right answer, okay? So what are we gonna do is we're gonna redraw our 5-membered ring. So I'm just gonna take this and tilt it on its side. So we're gonna redraw our 5-membered ring like this. We'll draw the double bond to oxygen, but we're going to erase the oxygen and we're going to put in a nitrogen. Okay, so that's going to be, let's say, this nitrogen, and what's it attached to? Well, it's attached to an NH2 group, put in our lone pair, and like I said, we call this a hydrazone. So hydrazine gives you a hydrazone. All right, so continuing on. The next one is a little bit more tricky, 19.20b, because in here, we're not going to form an enamine. An imine. We're going to form an enamine. Why? Because we have a secondary amine and we have a ketone, but now they're in the exact same compound. And so when we have the reaction between the nitrogen, so remember the first step of the mechanism is a nucleophilic attack by the nitrogen on the carbonyl carbon, the alpha carbon. So we end up forming a 5-membered ring. So let's get some practice on drawing a ring. So what I think the easiest thing to do would be, if I was just learning the subject, which we are, okay, is to draw the aromatic ring, okay, which is a 6-membered ring. There's no arguing that. Then what I would do is I would just draw a 5-membered ring attached to it, and then I just start counting. Say, okay, well, what is what? Okay, what's going to be attached to what? So let's try numbering everything. So if we have 1, 2, 3, 4, 5, okay? Carbon number 1 is attached to the nitrogen. So at number 2, this is where, actually, maybe I should number it the same way I had it down there. So let me just fix this. Okay, I'm going to number it in the same order I had it before. All right, so it's going to look like this. Just give me 1 second. All right, so it's going to look like this. So if I have 1, 2, 3, 4, 5. There, that's better. Now I fixed it. Okay, so carbon number 1 is attached to atom number 5, which is the nitrogen. So we put the nitrogen, oops, let me use black. So we put the nitrogen here, okay? Carbon number 3 has the 2 methyl groups attached to it, so we'll put those on here. And then the nitrogen also has an ethyl group attached to it, like this. Now, this is not an imine. If it was an imine, you'd have a bond here, but then that would mean there'd be a positive charge on the carbon, so that's not a thing. Remember, an enamine has a double bond between the alpha carbon and the beta carbon. Well, where is it going to be? It can't be to this beta carbon because this beta carbon already has 4 bonds. Therefore, the double bond has to be, there's no question, it has to be on this side here. And so that is the enamine that is formed in this specific case. So this is the enamine, and it is a cyclic enamine, right? But we still have to be able to kind of connect those dots and put compounds together like this. All right, there you go. So that's a little bit about imines, enamines, hydrazones that come from hydrazine. And then last class, we also talked about hydroxylamine, this compound over here, and how you can use that to make an oxime or an oxime, depending on where you come from, the way they pronounce it, like potato, potato. Anyhow, so let's move on from there. Then after that, we talked about the hydrolysis of an acetal, which is where we just take an acetal, put it in aqueous acid, and it converts it back to your aldehyde or ketone. You liberate your alcohol. So this is a very important reaction, and I'm talking about this reaction right here. And we said that acetals, as a matter of fact, are very resistant to basic conditions, and so they don't hydrolyze under basic conditions. We talked about the mechanism of the hydrolysis of an acetal and how it is just the reverse of the formation of an acetal. Then we talked about the hydrolysis of an imine or an enamine, and we said it's going to be the exact same thing. You're going to convert back to your aldehyde or ketone and liberate your primary amine. If you're hydrolyzing an imine, right, you'd liberate a primary amine if you're starting with an imine, and you would liberate a secondary amine if you're starting out with hydrolyzing an enamine, right? So the mechanisms for these reactions are just the reverse of the formation. So there's no need to really put them in the book. So where we started, where we kind of ended off was we looked at these first two hydrolysis problems. The first one was the hydrolysis of an acetal, right? So this carbon here is attached to carbon, oxygen, carbon, and here we have carbon, oxygen, carbon. So what I have here, this is an acetal. So we hydrolyze an acetal in aqueous acid. The next one is an imine. And so we hydrolyze that back to the ketone. So we got a ketone and we got a primary amine. And the next one is an acetal as well. It might be difficult to recognize it, but there is an acetal here. So if I use my black pen, you see that this carbon here, I'll put C for carbon, okay? That carbon is attached to carbon, oxygen, carbon. And we also have carbon, oxygen, carbon here. So what is my carbonyl, my aldehyde or ketone, going to look like in this case? Well, that carbon that I have in black, it's going to be attached to two hydrogen atoms, and it's going to have a double bond to oxygen like that. That's the simplest possible aldehyde in the universe, okay? That's formaldehyde. And then in this case, we're going to have a diol, which is going to have a total of 1, 2, I'll just number the carbons in the chain, I guess. 1, 2, 3 carbons in the chain. So if we have 1, 2, 3, we have our hydroxyl here and a hydroxyl here. But each one of the or carbon 1 and 3, they both have two methyl groups on them like this. So those are the two compounds that you would need. That's the diol and the aldehyde that you would need to make that acetal. And the last one is an enamine, right? We have a double bond attached to the alpha carbon, right? So this is an enamine. And so what are we going to liberate? We're going to liberate, in this case, a ketone and a secondary amine. So what's our ketone going to look like? Well, God help me as I try to draw it. It's going to look something like this. It's a bicyclic compound. But this is what the bicyclic compound would look like, and your double bond will be on this carbon. And then our secondary amine is going to be dimethylamine. Where's my black pen? There we go. Dimethylamine. It's going to be this secondary amine, just like that. There we go. So those are all hydrolysis reactions, right? And what do they all take? Whether you're hydrolyzing an acetal of imines, enamines, and acetals, okay? What do they all take? They all hydrolyze with H3O plus, just aqueous acid is what we use to do the hydrolysis of any imine, enamine, or acetal. The same thing would stand with a hydrazone and an oxime as well. They all hydrolyze with just aqueous acid. I think towards the very end of our last lecture, I mentioned that you can form a sulfur acetal. So it's an analog of an oxygen acetal. So if you have a cyclic acetal like this with oxygen in it, We just call that an acetal. If you replace the oxygens with sulfur, we call that a thioacetal. So thio stands for the sulfur atom. Okay, so a thioacetal. And it turns out that a thioacetal, unlike an acetal, can be reduced down to an alkane using what's called Raney nickel. And our textbook has a little bit of information about Raney nickel, how it's like a spongy nickel that has aluminum in it, I think, and it has hydrogen trapped inside the pores. Anyhow, the thing about Raney nickel is that it's pyrophoric, okay? Pyrophoric, which means it ignites on air. It ignites spontaneously in air. So it's kind of a dangerous compound to work with. So you can imagine we don't get students to work with Raney nickel a whole lot. But anyhow, also the mechanism is beyond the scope of our textbook. But it still is a great reaction because it provides you with another method for reducing a ketone or an aldehyde to the corresponding alkane. So now we have three ways. The first way is the Clemmensen reduction. And we also learned the Wolff-Kishner reaction. And then we also learned Raney nickel. So now we have three ways of doing that. So let's take a look at this question here. It's not meant to be anything mind-blowing. It just says predict the product for each of the following. And I think I might have done the first one and it got deleted or something. I don't remember. But anyhow, let's take a look at it again. So in the first step, we're taking this dithiol. So this is 1,2, you call this 1,2 ethane dithiol, right? It's dithiol because you've got two thiols in it. So 1,2 ethane dithiol. And then we have a catalytic amount of acid. And it doesn't say negative H2O in this step, but you do lose water in this step. So I'm going to write the intermediate that's formed, the thioacetal, in red, in my red ink. So it's going to look something like this. So we have an aromatic ring here. And then we're going to have our thioacetal. So that's after the first step. And then after the second step, when we treat that with Raney nickel, that's going to be reduced down to the alkane. And so that gives me this compound here. Okay. The next one is not a trick question. It's in the exact same vein as the first one. In the first step, you're going to make the thioacetal. So let's draw the thioacetal that would result. Here, you're going to have just a proton over here. And then we have our thioacetal like that. So after you treat it with Raney nickel, count your carbons very carefully, right? We have 1, 2, 3, 4, 5 carbons in the entire molecule. And so once it's reduced with Raney nickel, you get 1, 2, 3, 4, 5. So you end up with two. In this case, I don't know why you would do this reaction. It's kind of funny, but you end up with 2-methylbutane. 2-methylbutane. Just a little 3101 nomenclature practice for you there. All right. So give me a thumbs up if you're with me on the thioacetal, and then it gets reduced to an alkane with the Raney nickel. There's no mechanism. I mean, honestly, you guys, I worked as an organic chemist for most of my adult life. I don't remember the last time I used Raney nickel. It is used. It's not like it's an uncommon reagent, but I never used it much. And like I said, you have to be very careful with it because it can ignite in air. Anyhow, all right, let's move on to hydrogen nucleophiles. This section, believe it or not, is actually a review of Chapter 12. This is a review of the alcohols chapter. If you're saying to yourself, well, why do I have to learn it twice? Well, he put it in here a second time because in Chapter 12, you talked about alcohols, but in Chapter 19, you talk about aldehydes and ketones. So I guess it kind of feels like, well, he'd be remiss if he didn't mention lithium aluminum hydride and sodium borohydride reduction of an aldehyde or a ketone to give you an alcohol. So this is something, again, that we covered in detail. The only thing that I would add is that in my slides, in the second step of the LAH reduction, I always put H2O. That's from the old edition of the textbook, and there's nothing wrong with saying water, but I will accept, based off of the fourth edition, I will accept water or hydronium, just like the second step of the green yard. I will accept water or hydronium. Either one is perfectly fine with me, okay? So to reduce a ketone or an aldehyde, we can use LAH with it, which is, if you don't remember, this is lithium aluminum hydride. And then this one down here, NaBH4, that's sodium borohydride. And those are both good reducing agents for an aldehyde or a ketone. However, what you need to know is that lithium aluminum hydride is stronger than sodium borohydride. So you could just write here, lithium aluminum hydride, stronger than sodium borohydride, okay? And that's why it's a two-step process. The first step is the treatment with lithium aluminum hydride. The second step is adding water or acid. All right, whereas sodium borohydride, you can carry that reaction out in methanol. Also, you could do it in ethanol or even water. You could do this reaction in water and it will still work. Anyhow, but keep in mind that both of these reactions are done in a basic environment, right? There's no acid in the reaction environment. And so this mechanism here, again, was covered in chapter 12. Believe it or not, we looked at this mechanism in chapter 12. I do expect you to know this mechanism. This is like a sort of a Sparks Notes version of the mechanism. But what we see here in step 1 is we get the nucleophilic attack by our lithium aluminum hydride ion. We form a tetrahedral intermediate that we see here. And then in the second step, again, it's H2O. You could put here or it could be H3O plus. Either one is perfectly acceptable. And there you have it. So a very important mechanism that you have to know, lithium aluminum hydride reduction of a ketone or an aldehyde to give you an alcohol. Again, covered in chapter 12, but covered again here. And something that you want to keep in mind is what if you have an unsymmetrical ketone and you reduce that with lithium aluminum hydride followed by treatment with water or aqueous acid? Well, in that case, when you have the lithium aluminum hydride ion, ALH4, like this, okay, the hydride can attack from the front face of the molecule or it can attack from the back face of the molecule. And it's not going to be discriminant because this carbon is trigonal what? Trigonal planar. It is flat. And so, again, the nucleophile can come in from either face of the molecule. And so you end up with a racemic mixture in this case, okay? So you'd have to separate those in enantiomers if you needed to or something. Now, let's do some more review. So again, this is a review of, you guessed it, chapter 12, okay, the alcohols chapter. We talked all about Grignard, which should be capitalized for Monsieur Grignard. Anyhow, so a Grignard reagent will attack an aldehyde or a ketone, and you end up with an alcohol and a new carbon-carbon bond. So you can see here we have methyl magnesium bromide in the first one, and then that's going to do a nucleophilic attack. So just to practice the mechanism, the first step, we draw the methyl, remember, as a carbon ion. It's going to be a strong nucleophile. We're going to get our nucleophilic attack like this. And then in the second step, it says water. And again, I would accept aqueous acid as well. Either one is perfectly fine, okay? The next one is the same thing as well. We have our aldehyde. This is butyraldehyde. If we treat this with methyl Grignard, the methyl group is going to attack the carbonyl carbon. Then after a proton transfer with water or H3O plus, we end up with a secondary alcohol. So keep in mind that a ketone will give you a tertiary alcohol, whereas an aldehyde, when you do a Grignard, will give you a secondary alcohol. Okay, so that's the result of the Grignard reaction. And again, you see racemic here. Why? Because the nucleophile is not going to discriminate. It can attack from either face of the molecule. Now, as far as the mechanism goes, this is just a Grignard mechanism. Again, we covered this in depth in chapter 12. So this is covered in chapter 12. We said you have your nucleophilic attack in the first step. The second step is a proton transfer. Again, it could be water or it could be H3O plus that transfers the proton. Either one is totally fine. It doesn't matter. But remember, it's a two-step process, right? You can't write, it would be very wrong to write something like methyl magnesium bromide on the top of the arrow and then H3O plus on the bottom. That's a huge no-no. Right? You have to be sure to put this is step 1, this is step 2, right? You have to be very clear that these are two different steps. If you were to combine the acid with the Grignard, it's just going to destroy your Grignard. And that's one of the reasons why we have to keep our glassware so dry. We have to remove all traces of water from our reaction flask when we're doing a Grignard reaction. All right, so That's a little bit of review of hydrides, lithium aluminum hydride, and green yards. Now we're going to get into something new. Okay, I promised you something new today, and here it is. And the first new reaction that we're going to look at is the formation of a cyanohydrin. Okay, cyanohydrin, brand new functional group. In case you haven't noticed, there's a few new functional groups in this chapter, isn't there, right? There's quite a few of them, as a matter of fact. Imine, enamine, oxime, hydrazone, acetal, hemiacetal, thioacetal, carbanolamine, right? All these different things that we've talked about. Well, a cyanohydrin is an important functional group to know. And in a cyanohydrin, you have a carbon that has a cyano group and a hydroxyl on it both. Okay, so we call it a cyanohydrin. And there are a variety of ways to make cyanohydrins. And our book mentions like a whole pile of them. The first one that he mentions is this one right here. I'm not sure why, but my guess is that it's historical, that this is probably the first way that people made cyanohydrin. So it's by taking a ketone and treating it with hydrocyanic acid. The problem with hydrocyanic acid, I don't know if I wrote down the boiling point in here. Let me just double check something here. A cyanohydrin. I thought it said it here in the textbook. Yeah, it says here the boiling point of HCN. So let me just pencil this in here for you. The boiling point of HCN is 26 degrees Celsius, okay? It's warmer than 26 degrees Celsius outside today. And so the idea is that HCN is a poison gas, okay? That's what they execute people with, or they used to in the gas chamber in California. It's a very dangerous gas to be messing around with. So you can imagine if you're in a hot laboratory, working with HCN gas is a nasty thing to work with. So if you're like, well, why would anybody want to do this then? That's a good question. That's pertinent. The reason why is cyanohydrins can be used to do a whole bunch of cool stuff, okay? A good scientist should never use the word stuff or thing, but I think it's appropriate at this point. Anyhow, so here is the mechanism of cyanohydrin formation under basic conditions. So what they found is that this reaction here is actually really slow. Okay, it's a very sluggish reaction. And so I forget who it was, but somebody discovered that if you put, I think it's Arthur Lapworth maybe, that if you take a tiny bit of base and you put some base in here, then you have some cyanide ions as well, and that you end up with a much faster reaction. So this is the mechanism when you have a catalytic amount of base in with your HCN, right? Because you have some cyanide ions, it does a nucleophilic attack, then you just get a proton transfer, and you don't even have to do a second step, right? It's just done after the first step. However, again, you have to use HCN, and I just told you how nasty HCN is. So, like, okay, well, could we fix that up? Well, to achieve those basic conditions, if you're wondering, well, how do you do that? Like, what do you do? Normally what's done is that you mix potassium cyanide, and if you're like, is that the potassium cyanide? Like, don't drink the Kool-Aid. That's exactly what it is, okay? So you mix potassium cyanide with hydrocyanic acid, HCN, and then you get your cyanohydrin, and you see it works in a really good yield, as it does in this reaction as well. However, I didn't put this in the textbook, but I want to put it in here for you, okay? Is that the book actually mentions another condition, which it doesn't put in the slide. So I'm going to write it. So make sure you make this note. Book, your textbook, book uses this. In step 1, he uses potassium cyanide, or sorry, my mistake. The better conditions is just this. It's a mixture of potassium cyanide and HCl, okay? This is what he says. After enough research, people found that this is the best way to do the reaction. Why? Because you avoid having any HCN, which is highly toxic, okay? You don't have any HCN gas to worry about. So that way you only have to have some potassium cyanide, which is somewhat, dangerous. But yeah, so if you're wondering, you mean this reaction, instead of using KCN and HCN, you could write KCN and HCl mixed together. Yes, it would work that way. I guess I should use a comma instead of a slash. But yes, that would work. Okay, same thing here. I'm going to post this to the internet. Okay, so you can throw it in my face if I don't accept it. KCN and HCl mixed together. And I think that that's actually a better way of doing it. Again, all of these ways work, and I find like it's an awful lot of information for students. But again, I think that this is the best way to do it is using potassium cyanide and HCl. Why? Because I'd be afraid of using HCN gas. That doesn't sound like a whole lot of fun to me. So now that we've learned how to make a cyanohydrin, this is a cyanohydrin. Okay, there's a cyanohydrin. What can you do with a cyanohydrin? Well, lots of things. The first reaction shows you the reduction of the nitrile group with lithium aluminum hydride followed by water. And again, you could put here or aqueous acid. And that gives you an amine. In this case, you get a, well, I guess it's written over here, you get a primary amine. Or you can just hydrolyze it with aqueous acid. This is a cool reaction. This reaction we cover in detail in chapter 20. So there's no mechanism for it in this chapter, but you hydrolyze the whole thing all the way to a carboxylic acid. And I know you're already busy in your brain with learning all the reactions in this chapter, but just to kind of put this bug in your ear, what's cool about carboxylic acids is those are covered in detail in chapter 20, and there are a lot of neat reactions that you can do with a carboxylic acid. So just something to think about ahead of time. So now that we've covered cyanohydrin, so what have we covered that's new today? The only thing so far I'd say that we've covered that's brand new that I didn't even review at all last class would be the cyanohydrin. But the next reaction, the Wittig reaction, is a way to make carbon-carbon bonds, just like we did in the cyanohydrin, right? If you look at it in a cyanohydrin, you find a way to make a bond between carbon and another carbon. So that's a very cool thing, okay? But now with Wittig, we find another way to make carbon-carbon bonds. And this is one of the most popular reactions in all of organic chemistry. And the inventor of this reaction is Georg Wittig. So Georg Wittig. And he won the Nobel, so he got Nobel Prize for this reaction, Nobel Prize in 1979. He shared it with a guy named Herbert Brown, anyhow, that year. But yeah, so very, very important reaction. I mean, you win a Nobel Prize, you must have done something that makes a lot of people happy, you know, in terms of chemists. You know, a lot of people just love you and adore you for what you've done, you know. Oh, you made my life so much easier. I couldn't find a way to make this carbon-carbon bond, but now because of you, Dr. Wittig, I know how to do it using the Wittig reaction. So it says here, extremely important reaction. If you look at any ACS study guide or MCAT materials, they always bring up the Wittig reaction. Why? Because it's so important. And what makes it so great is, like most Nobel Prize winning reactions in organic chemistry, it finds a way to alter the carbon skeleton, okay? So we get to build on a carbon skeleton. And so what we do, the reason why it's in this chapter, why is it in chapter 19? Well, it's because your starting material is a ketone or an aldehyde, okay? We start it with a ketone or aldehyde, and then we convert it into an alkene. So this is chapter 19, and then we converted it into an alkene, which we covered in chapter 8. So you guys definitely know what a carbon-carbon double bond is here. So the Wittig reaction, sometimes it's called the Wittig, come on, pen. Sometimes it's called the Wittig olefination, OLEFINATION, okay, the olefination. The reason they call that is because alkenes, another name for alkenes is olefins. It's an old word. It's an old word, get it? But anyhow, olefins is an old word that we use for alkenes, so that's why they used to call it the Wittig olefination, but we just call it the Wittig reaction most of the time today. So here you see some ketones, here you see some alkenes, and if you're looking at it and going, what is this weird looking thing here, okay? Well, you guys probably remember that when you have a compound that has both a positive and negative charge in it, we call that a zwitterion. True, we do. But when it's a Wittig reagent that has a positive and negative charge in it, we call it an ylide. YLIDE. Is that a weird word or what? An ylide, okay? The ylide. Okay, so this is an ylide, and this is obviously an ylide here. And if you unpack the ylide, so you have a carbanion over here, a carbon with 3 bonds, 1, 2, 3, 1 lone pair. And then phosphorus, which is in the same group as nitrogen, right? When phosphorus has 5 valence electrons, so 5 valence electrons subtract 1, 2, 3, 4 bonds gives you a formal charge of +1. So if you have +1 and -1 in the same molecule, the overall charge of the ylide is 0, right? It's completely neutral. So there's nothing wrong with drawing it that way. Now, if you're looking at it and saying, well, hold on, why do you draw it like that? Why don't you just cover these things up, take this lone pair and make a double bond? That would be reasonable. And you'd be right, okay, because phosphorus is in the 3rd period, right? So phosphorus can expand its octet, and there's nothing wrong with drawing carbon with a double bond and 2 single bonds. If you're wondering, why don't you draw it that way? Well, number one, it's not true. We do draw it that way sometimes, okay? And you see it over here. Here is our ylide, okay? And this form over here, it's got its own name. It's called the ylene form. Now, again, if you're looking at this and going, why the hell do you not draw it like that? Like, why would you choose to draw it as this zwitterion, this ylide thing? It's a good question. Remember that carbon is in the 2nd period, whereas phosphorus is in the 3rd period. So what does that mean? Okay, I'm going to draw something and then I'm going to erase it. Period. Okay, there we go. It's because the orbitals that are used to make the pi bond, remember you make a pi bond from the overlap of 2 p orbitals side by side and they overlap. Well, the thing is that the carbon's 2 p orbital is like this, and then the phosphorus is like this. So do they overlap? Yes, to some degree, but the overlap is really crummy. It's a fancy word would be inefficient, okay? So again, the ylide is a neutral compound that has a negative charge next to a positive charge. The negative charge is on the carbon and the positive charge is on the phosphorus. Now the mechanism, you guys remember cycloadditions, when we look at Diels-Alder, that was a 4 + 2 cycloaddition, right? You had 4 atoms in the transition state from your diene, and then you had 2 atoms in the transition state from your dienophile, right? But now it's going to be a 2 + 2 because we're going to have a reaction between the 2 atoms, the carbon and the phosphorus, and then the carbon and the oxygen from your aldehyde or ketone. Okay, so let's take a look at what this reaction mechanism is going to look like. And believe it or not, I think you should actually have an idea how to draw this mechanism. Okay, the first step, you can see that whoever did this mechanism drew it as the ylide. Now the carbon in the ylide has a negative charge. And you guys know that if we look at the carbonyl in detail, right, you guys know that the carbon is delta plus and the oxygen is delta minus. So it makes sense that the negative charge on the carbon, the lone pair on this carbanion, is going to attack the electrophilic carbon, right? This carbon right here, okay? And then instead of taking these electrons and putting them on top, we take them and we make a bond with the phosphorus. So it's a 2 + 2 cycloaddition, and we end up with a 4-membered ring, right? 1, 2, 3, 4, this tiny little ring that we call an oxaphosphatane, okay, an oxaphosphatane. And when the oxaphosphatane breaks, you see we make a double bond between this carbon and this carbon, and then we make a double bond between the phosphorus and the oxygen. So we end up with an alkene, and we call this triphenylphosphine oxide. Triphenylphosphine oxide, or for short, we call it TPPL. Triphenylphosphine oxide. It's really the bane of organic chemists. It's very difficult to get rid of triphenylphosphine oxide from a reaction mixture. So before we move forward, I just want to share one thing that I don't talk about a lot in this class. Like I'll talk about how if you form a gas, it can be the driving force for a reaction based on Le Chatelier's principle, but I don't really bring up specific compounds that are the driving force. But I'll tell you right now, if you want to remember something, the triphenylphosphine oxide is very stable, and it is what drives the formation of the alkene, right? The forming of the triphenylphosphine oxide, right? It is so stable, right? If you think about your potential, it is so stable that it is what pushes the reaction forward. It's the driver of the reaction, okay? It's the formation of triphenylphosphine oxide. I'll be honest, I've never really tested my students on that. I don't think, maybe in the majors class. But if you can remember that, it's the formation of this compound that pushes everything forward. So there you go. Now, when it comes to your Wittig reaction, remember this thing here, the ylid? Okay, let's back up for a second. Let's take a look at our ylid in detail. Okay, if we look at these ylids here, okay, because this ylid is the same one that's shown here. Okay, so it just keeps repeating the same one for quite a while. Let's take a look at what's happening. When you're drawing the product, if you want a shortcut, students always like shortcuts, and I don't blame you, I do too, okay? If we look at the ketone, all you have to do is to draw the product, is draw everything, but don't draw the oxygen on the end of the double bond, okay? So I've just drawn this, and I leave the oxygen out. So if you're wondering, well, what goes here? All you do is look at what's attached to the phosphorus. It's a CH2 group, and then you just write CH2, and you're done, right? See, it's just a CH2 group there. Same thing for the next one, right? We're going to write down all of this, except we're not going to write in the oxygen. So we'll write down the six-membered ring, put the double bond. We don't put the oxygen. What do we put? Everything that's attached to the phosphorus, it's going to be a CH2, like that. Give me a thumbs up if you're with me on my method for drawing Wittig products, right? Just leave the oxygen out. Just look at what's directly attached to the phosphorus, and that's what you put in its place. Cool. So we've gone over the mechanism. Now, when it comes to doing the Wittig reaction, not only do you have to understand how the reaction works, you actually have to understand how to prepare the ylid, okay? This is very important. This is always tested by ACS. They'll give you two routes. So where we're going to, if you're looking ahead, is to a question like, where is it? Not that one, not that one, not that one, not that one, not that one. More like this one here. So 19.38. This is what we're working on right now, is identifying reagents that you would use to prepare each of the following compounds via a Wittig reaction. So not only do you have to know the Wittig reagent, you have to identify reagents that you would use in the Wittig reaction. So let's go back and let's see what we mean by that, okay? If we take a look at, where was it? This example right here on slide 77, okay? Give you a second to get caught up here. Okay, so what it's saying is this, is that you've got to synthesize your Wittig reagent. You've got to make this from some starting material. So how do you do that? Well, the first step is to take an alkyl halide, okay? And you treat that with this compound here. This is called triphenylphosphine, okay? So PH3, this is called triphenyl, right? Three phenols, triphenyl, and it's got a phosphorus, so it's a phosphine. So triphenylphosphine, okay? Well, you can see that triphenylphosphine has a lone pair on the phosphorus. It's a good nucleophile. If you have methyl bromide, that's a really good electrophile. You get an SN2, and then you would end up forming this salt, okay? So you think about this. You displace the bromine, so the carbon has no charge, but now your phosphorus has 4 bonds and no lone pair, so it's got a positive charge, and you've released the bromine. This is a salt. This is not an ylid. This is not an ylene. This is not a Wittig reagent. What do we have to do? We have to remove a proton. And so the base that we're using here, this base is called, I'll use blue ink. This is called butyllithium, B-U-L-I, butyl lithium, right? You have the butyl carbanion, and then you have the lithium cation. And the butyllithium is a really powerful base. It's going to rip the proton off of that carbon to make the Wittig reagent. So now we have a carbanion and we have a positively charged phosphorus, like that. Not only do you have to know how to put this together, so first is triphenylphosphine, the second step is going to be the butyllithium. You've got to remember that this reaction, this first reaction, is an SN2 reaction, okay? So what does that tell you about your alkyl halide? Is that it's going to be best if it's methyl or primary. Secondary will work some, and tertiary is not going to work at all. Okay, you're going to get no SN2 on a tertiary alkyl halide. So there we go. All right, so the Wittig reaction is particularly useful. Why? Because it makes a new carbon-carbon double bond at a very specific place, right? Here's your double bond. Now what you can do is you can replace that oxygen with something that is carbon-based. So here's our Wittig reagent here. This is the ylene form. They could have drawn the ylide, but they didn't, okay? But if we wanted to draw the ylide, it would look something like this. Okay, where we have our, come on, where we have our proton. Here we have our methyl group over here. We've got our positive charge here and our negative charge like that. So that is the ylene form, and this is the ylide form. Again, I'm not going to make you pencil out this mechanism, but if you have some little tiny group attached to your, especially if it's a simple alkyl halide that forms the Wittig reagent, then in that case, you're going to end up with the Z product. Okay, so let's highlight what's important here. If you have a simple alkyl halide as your starting material, you're going to form the Z alkene, the zusammen together. Or this one, you can see it's also cis. Anyhow, however, if you have something that can stabilize the negative charge, here we have an ester group that can stabilize a negative charge. Here we have a whole aromatic ring that can stabilize a negative charge. If you're unsure as to how this can stabilize a negative charge and this can stabilize a negative charge, the answer is just resonance, right? I don't have time to go over all this, but if we just drew this one here, okay, if we drew it as the ylide form, it would look something like this. So we have CO2 ET, okay, and then we have something that looks like that, and then we have the negative charge over here. Well, you can see that this is resonance stabilized because if I draw the ester group, it's going to look like this. And we can draw a curved arrow like this, where we delocalize the negative charge. So we'd end up with something that looks like this. We'd end up with a double bond here. All right, something like that. Okay, those are the resonance forms. So we call that a stabilized ylide. Why? Because the negative charge on the carbon is stabilized. And you could also do the same kind of exercise with that aromatic ring. Well, in that case, you get the E product as the major product. All right. Now, the real rationale as to why this happens with an electron withdrawing group is actually, it's not super complex, but it's beyond the scope of our class. So I'm not going to ask you for an explanation. What you need to know is that if you have a simple alkyl group, you're going to get the Z product. And if you have something like an ester or an aromatic ring that can stabilize the carbanion, in that case, you're going to get the E product, the Entgeg and the Epicent. Just give me a couple more slides and we'll take our first break. It says here, electron withdrawing group, like a phenyl ring, delocalize the anionic charge, stabilizing it. And so in that case, you end up with an E product. Well, there's another reaction that is very similar to the Wittig reaction. Sometimes we call it the Horner-Wadsworth-Emmons modification of the Wittig reaction. So here is a stabilized Wittig reagent, or sorry, here is a stabilized Wittig reagent. Sorry, my mistake. Over here, again, repeating myself, this is stabilized. Why? Because you can draw a resonance form like this. Well, the one on the bottom right is a Horner-Wadsworth-Emmons reagent, okay? And it also kind of looks like a stabilized Wittig. Why? Because you could draw curved arrows like this. You could draw a curved arrow like this. But either way, it's highly stabilized. And since it's highly stabilized, it gives you exclusively or almost exclusively an E alkene as your major product. So here's the Horner-Wadsworth-Emmons here. So if you're wondering, well, how do I draw this product? How am I going to figure this out without drawing the mechanism? Let me show you my shortcut. Here's what you're going to do. You're going to take this aldehyde. You're going to redraw it. Okay? Then you're going to erase, you're going to erase the oxygen like that. Then you look at what's attached directly to the phosphorus, CH2, and all of this ester over here. So you're going to have CH2. I guess in this case, it's just going to be a CH, but you get my drift. So you have CH2. And then we have 1, 2 carbons, and then we have our ester like that. So there you go. There's the Horner-Wadsworth-Emmons modification. And if you're wondering, can we affect the stereoselectivity, right? Because you guys know that E and Z and cis and trans, those are diastereomers, so they're types of stereoisomers. And so if you're wondering, can I affect the stereoselectivity of the reaction to give me more E than Z or more Z than E? The answer is yeah, but that's, again, pretty complicated. That requires a use of certain Lewis acids and things like that. So we don't cover that. But here is, again, this is the kind of question that they ask on the ACS, ACS, or MCAT, or DAT, etc. Is what they do is they start out with this compound and say, you want to make this compound. So what would this be called? This would be called 2-methyl-1-butene. So 2-methyl-1-butene. All right. And there's two possible ways. You could make it from the ketone here. That would be 2-butanone plus this Wittig reagent. Or you could make it from this Wittig reagent, formaldehyde. Okay. So one of these is a good route and the other one is a bad route. The way I want you to remember which one is a good route is like this. If you think about just the Wittig reagent, that has to be formed via an SN2 reaction, right? This reagent has to come from an SN2 reaction. Which one of those is going to make an easier SN2 one? The one on the left or the one on the right? Could anybody answer that? You might have had to have read ahead like a page or two to figure this out. But could anybody tell me which one of these would be easier to do an SN2 with? The one that has a methyl group on it, the CH2, or the one that has the butyl group on it? Yeah, thanks, Rachel. Absolutely. Son of a gun. This one is going to work much better. So we'll do like the Drake meme here. We'll go like check mark on this one, like no with this one, okay? So the one in route 1 is going to work much, much better. So we take a look at the two, okay? So this is what Rachel was referring to. She said, if I have, let's say, methyl bromide or methyl iodide, and I try to do an SN2 on it, let's think about this. I've got CH3, I don't know, let's choose iodide, okay? Then I've got triphenylphosphine, so PPH3, got my lone pair. Well, this reaction is this SN2, nucleophilic attack and loss of leaving group, is going to work really, really well. Whereas the one on the bottom, right, if I redraw my alkane, which looks something like this, right? If you take triphenylphosphine and try to react with this, that's not going to work well at all. Why? Because this one here is methyl, and this one here, this is a secondary carbon. Okay, and so a secondary carbon is going to react much slower. So this is going to be, this reaction here will be fast, and this reaction here will be very slow. Okay, so after you've done the first step, if you need a little practice, what you're actually going to end up with is this, is you're going to have triphenylphosphine, and then you're going to have CH3, so you have a positive charge here, plus iodide. That's the phosphonium salt. And so what you're going to do in the second step is that the butylithium, right, your butylithium, so I'll just put butane carbanion, is going to remove this proton, and you end up with your ylide, which can also be written as an ylene. So that's what's going on here in the Wittig reaction. You have to not only know how to do the Wittig reaction and draw an oxophosphate and the mechanism and everything, but you have to understand where the Wittig reagent comes from and how to make it. What's the best way to make it? So overall, here's the Wittig synthesis. First step is to take iodomethane, treat it with triphenylphosphine, right? That gives you the phosphonium salt. Then you use butylithium to remove a proton. That gives you, in this case, the ylene. And if you want to draw the ylide, it's the exact same thing. So you'd end up with this. Okay, there's the ylide. So I could write that here, ylide. And then that's going to react with the carbonyl. And in this case, there's no E or Z to consider because this carbon has 2 hydrogens on it. So there's no E or Z that exists in this particular reaction. So what we're going to do now is we're going to take a short break. And when we come back, we're going to try these questions that deal with Greenyard chemistry. So again, that's a review of chapter 12. Then after that, we'll take a look at these reactions here. So these ones actually both involve Greenyards as well, I think, just by inspecting them quickly. This one here involves a cyanohydrin. At least cyanohydrin, there we go. At least it does in the first step. The second step is the hydrolysis of the nitrile. One. The next one also involves cyanohydrins. The next one involves Wittig. And this would be the Horner-Wadsworth-Emmons variation, I guess, on the Wittig reaction. This one here, again, a Wittig again. So this is also a Wittig reaction. And then after that, we're going to be on the last section, which deals with Baeyer-Villiger oxidation. So 19.11 will be our last section in this chapter of new chemistry. In this chapter, I guess, is more proper.